So welcome to this first video in what I hope is going to become a playlist on measure theory. So in this first video we're not going to discuss the bigger picture of what measure theory is all about. We're going to start with a definition, one of the foundational definitions that we're going to need in building measure theory, and that's the definition of what is meant by a semi-algebra in measure theory. And then in a subsequent video we'll look at what is meant by an algebra and then what is meant by a sigma algebra. So semi-algebra, algebra and sigma algebra are going to be really important concepts in measure theory. So a semi-algebra then, so it is a special collection of subsets of a set. So whenever you talk about a semi-algebra or an algebra or a sigma algebra, you need to have some sets that these things are from. So we'll call our set the set X. So this could be a finite set, it could be an infinite set. And I might just take an example. So we'll take initially a finite set example. So we could have just a few elements in this set. I can make them whatever symbols I like. So I've put the symbol A, I could put the symbol 2 in, I could take a Greek symbol, zeta. So I'll just have 3 things in my set. So this is my set X, but in reality, when we get onto proper measure theory, these are going to be much more complicated sets. They're going to be sets like the real numbers, or R2, or R3, or C3, or something along those lines. So much more complicated sets, but we'll start off simple with just this finite set of 3 elements. Then, a semi-algebra of this set is a subset of the power set of X. So we can denote our semi-algebra by S, and it is going to be a subset of the power set of X. Now, I will denote the power set of X with this curly P here. And remember, this means the set of all subsets of X. So in that you'll have the empty set, which is a subset of X. You'll have all of the singleton sets, so the set with A in it, the set with 2 in it. And remember, this symbol here, phi, this just means braces with nothing in. So that's the only combination of a set with nothing in. Then we'll have all combinations of sets with one thing in, so A, 2, and then the set with just zeta in. And then we want all sets that just contain 2 elements. So A and 2 would be 1, then A and zeta would be 1, and then 2 and zeta would be 1, and then finally you'll have the set that contains all 3 elements. I think that's all the sets that contain 2 elements, yes, so we've got both of the ones that contain A and then we've got the other one that doesn't contain A, yes, so that's all the things that all the sets contain just 2 elements, and then you'll want the set containing everything, which we could write out in full, or we could just put X there. So this is the power set of X, and you can see it's got 1, 2, 3, 4, 5, 6, 7, 8 things in. So 2 to the power of 3, because you can either include this or not include this, you can include this or not include this, include this or not include this, so it gives 2 times 2 times 2 different options, 8. So a semi-algebra is going to be a subset of this. So we're going to take a bunch of these, maybe not all of them, and put them into a set, and this is the sort of thing we're going to be working with when we're talking about semi-algebras and sigma algebras of a set. They are subsets of the power set of that set. Now, it's not enough just to be a subset of the power set of X. You know, if I took, for example, this, I took the empty set with the singleton set A in, I do not believe that that is going to be a semi-algebra. No, it's not going to be a semi-algebra. So that's a subset of the power set, but it's not a semi-algebra. So I need to tell you more about what is meant by a semi-algebra. So there are a bunch of rules that your subset needs to obey in order for it to meet the criteria to be called a semi-algebra. So there are 3 rules in total. Firstly is that the empty set and the entire set must be elements of your set S, which we're going to say is going to be a semi-algebra. So that's the first thing that this fails on. The whole set is not in there, so this can't be a semi-algebra. So let's add in the whole set, because even with the whole set in, it's still not going to be a semi-algebra, but we'll see which rule it then breaks. So now it's got the empty set and the whole set in, and the singleton set containing A, this set, which we'll call S, is still not going to be a semi-algebra because it's not going to satisfy some of the later rules. So the second rule is that if you take finite intersections of elements in the set, then the thing that you end up with will also be in the set. So we can write that quite simply. If E1 and E2 are elements of your semi-algebra, then if you intersect the two of them together, E1 intersect E2 is also an element of the semi-algebra. So take any two elements of your set. If you intersect them together, you must also get something that's in your set. That's one of the criteria in order to be called a semi-algebra. So does this thing that we've got here obey this? So let's take all combinations of two things from here and try intersecting them. So the empty set intersected with this singleton set is just going to be the empty set, so that's fine. The empty set intersect with X, again, is just going to be the empty set, so that's again fine. A intersected with X is just going to be A, so that's fine. And then I suppose you could intersect all of them with themselves, but then you'll just get themselves back again. So actually this set that I've got here does obey this criterion, so it's not this criterion that it's going to fail on. And note, once this is true, it then follows that finite intersections are going to be contained within the set, because, you know, if I have something like, let's say I have E1, E2, and E3, those are elements of S, then if I consider, well, actually I'll write this out in a fancier way, if I consider the intersection of all of these, in fact I could make this, well actually we'll just start with 1 to 3, intersection from I is equal to 1 to 3, i.e. E1 intersect E2 intersect E3. Well, the reason that this is now also going to be contained in S, if what I've written out here is true, is because you can associate the intersections. So, you know, this means all the things that are contained in every single one of those sets. But if you take all the things that are contained in E1 and E2, and then say, let's intersect that with E3, then everything you're going to end up with here is going to be the same as what you would end up with here, because you're saying, take everything that's both in E1 and E2 to create this thing, and then take everything that's in that is also in E3. So that means it's going to have to be contained in E1, E2, and E3, which is exactly what this means. And similarly, you know, if you took it up E1, E2, all the way up now to En, where n is some finite natural number, and you considered the intersection from I is equal to 1 to n of Ei, if this is true, it's going to then imply that that this is true, that the intersection, this finite intersection, is going to be an S. And I think actually I probably didn't quite finish the explanation. So we're saying that if this is true, then this is true. So the reason is because this is equal to this, and then because this is true, we know that E1 intersect E2 is going to be in the semi-algebra, E3 is in the semi-algebra, so then we've got something in the semi-algebra intersect with something in the semi-algebra, and then again by this. So we just apply this twice to conclude that for the intersection of three things in the semi-algebra, you end up with something in the semi-algebra. And now, in the case of intersecting n things in the semi-algebra, we'll just apply what we've got written here n times now to conclude that this intersection must be in the semi-algebra, because this is equal to E1 intersect E2, which will be in the semi-algebra, then intersect E3, that thing will then be in the semi-algebra, then intersect that with E4, that thing will then be in the semi-algebra, and you continue this on n times. So formally, you know, by induction, it follows, by, you know, the logical axiom of induction, it follows that from the fact that if E1 and E2 are in the semialgebra, we know that E1 intersect E2 is in the semialgebra, that if you have a finite intersection of elements in the semialgebra, that it will also be in the semialgebra. So that's property number 2 of semialgebras, and then that took up quite a lot of space. I would like this third property to be nearby, or not red doesn't show up very well, 3 here. So I'm just going to circle these in blue here. So we've got 1, 2, and now we're going to have the third property here, which is that if E this is the third and final property that your collection of subsets must obey in order for it to be called a semialgebra. So if the subset E is an element of your semialgebra, then if you take E complement, meaning the complement of E in the whole set X, so X subtract E, which we could just write E complement like that, as long as we know, that we're always working inside the large set X, then E complement must be made up of a finite disjoint union of elements of the semialgebra. So this is actually the crucial difference between an algebra and a semialgebra. In an algebra, it's actually simpler. In an algebra, you take these first two properties that we've just been through here, and then you just finally insist that E complement must also be in the semialgebra. So if E is in the semialgebra, E complement must be in the semialgebra. Here it's slightly more complicated. You don't quite insist that. Instead, you insist that E complement, or actually I'll write this differently, that there must exist some elements. What should we call them now? Let's call them A. So a finite number of elements, A1, A2, all the way up to AN, that are elements of the semialgebra, such that they're all pairwise disjoint. So AI intersect AJ is equal to the empty set for IJ is equal to 1, 2, all the way up to N. So take any two of them, intersect them, and there is no intersection, it's empty. So they're pairwise disjoint. So there exists this finite bunch of sets in your semi-algebra that are all disjoint such that E complement is the union of these. And of course, because they're all disjoint, it's going to be a disjoint union. So I'll use the disjoint union symbol, which is this squarey symbol. So union from I is equal to 1 to N, disjoint union of AI is equal to E complement. So E complement doesn't have to be in the semi-algebra, but you have to be able to build E complement out of things that are in the semi-algebra, where these things in the semi-algebra are all pairwise disjoint, and you have to be able to do it out of a finite number of them, not a countably infinite number, or even worse, an uncountably infinite number, a finite number. So that's the third and final property of semi-algebra, and I think this one is where this set still fails. So for example, these two are fine because, the empty set's complement is the entire set, so its complement is actually in the semi-algebra, so you can just take you just need one A here. You set A1 is equal to X, and then you don't need any more. That certainly means that you can build its complement out of a finite bunch of things in the semi-algebra. So if the complement is in the semi-algebra, that's the easiest case, basically. It definitely satisfies this. And similarly, X, if you take its complement, it's the empty set is in here, so again, you just need one here, one of them, to build the complement in that case. The problem, of course, is this singleton set here, because its complement is going to be the set containing 2 and zeta, and I cannot build this set out of a disjoint union of finite things in here. Neither of these two sets contain these elements, so the only option is to take X, but X has too much in it. It has A, so you can't build its complement out of things that are in the set. So how could we fix that? Well, one thing we could do is we could just stick this set straight away into there. Then we'd have to check that it still obeys property number 2 if we did that. So if we took that collection of subsets, so the empty set, the whole set, the set containing A, and the set containing 2 and zeta, so obviously it's going to obey this. Is it still going to obey this, that if you intersect any of the two things? So let's check. So we don't need to check the combinations that we've already been through. So we just need to check the new combinations, which is intersect this one with all the other things. So if you intersect this with this, that's fine, you'll get the empty set. If you intersect this with this, that's fine, you'll get the empty set. If you intersect this with this, you'll get it. So actually that's perfect. So this subset we've got here does work. All the complements, we've discussed how these two are fine, and then these two are also now going to be fine because they're complements to each other, so their complements are going to be in the set, just like these ones' complements were in the set. So actually it obeys a higher definition. It obeys the definition of an algebra. And in fact, actually, this kind of makes the video that I was going to make. I was going to have the definition of an algebra separate to a semi-algebra, but actually I'll just make this video on semi-algebras and algebras because, frankly, the property only a tiny bit changes. So we've just seen the definition of a semi-algebra. All you need to change, you don't change number 1 and number 2. All you change is this one, and you insist in an algebra rather than a semi-algebra that E complement is an element of the semi-algebra. So if E is an element of the semi-algebra, E complement is also an element of the semi-algebra. So much simpler than this definition for semi-algebra. So this example we've got here, it is a semi-algebra, but it's stronger than a semi-algebra. It's an algebra because all the complements are actually in the set. Could we give an example of something that is a semi-algebra but is not an algebra? Let's take, for example, I don't know if this is going to work, but let's see if it does. We'll go over here. I think if we take the set that contains the empty set, the whole set, and then all the singleton sets, that might work. So A, 2, and zeta. So let's have a look at this. Obviously the empty set and the whole set are in there, so we don't need to worry about that. Now we need to worry about intersections. So I think it's reasonably obvious, you know, if you intersect the empty set with any of them, you'll get the empty set, so that's fine. If you intersect X with any of them, you'll get the other thing that you're intersecting it with. So if you intersect X with this singleton set, you'll get this singleton set, which will then be back in the set. If you intersect this one with these two, you get some, we've already gone through those, you get something that's back in the set. If you intersect it with these two, you'll get the empty set, and then you can see that will continue on. So if you go to any of the singletons, yes, if you intersect them with anything, it'll again be back in this set. So it obeys property number 2, and then we can see that it's also going to obey property number 3, not the algebra property number 3, but the semi-algebra property number 3. So these two, their complements obviously remain each other, and therefore they're back in the set. These ones' complements, you can build them out of a finite disjoint union of other things in the set. So this one's complement is the union of this one with this one. This one's complement is the union of this one with this one, and this one's complement is the union of this one with this one. So there's an example of a subset of the power set of my set that is a semi-algebra. So I think with that we are close to finishing. I'll just recant the definition. So apologies that this video was not particularly planned out. I changed my title for the video halfway through, so it's been on both semi-algebras and algebras. So to summarise, these are special classes of subsets. In fact, that's an excellent word. When you've got a set where the elements of the set are sets themselves, then you can call that a class of subsets. It's a word we often use in mathematics. So a set of subsets, we often call it a class of subsets. So these are special classes of subsets of a set. So you start with your set, which I took as this finite set, and then if you want to build a semi-algebra or an algebra of this set, then you need to create a class of subsets of it, which is going to be a subset of its power set. For a semi-algebra, the the properties that it needs to obey are that the empty set and the whole set are in it, and we denote a semi-algebra by S, and we denote an algebra usually by A. And we should try, or at least in measure theory, often you try to make these sort of classes of subsets, you try and make them very curly. So I might try and make the S curly in this way by putting little curls on the end, and then I should try and make the A curly for algebra as well. So maybe I'll do it like people usually, sorry, the iPad's lagging, the heat. Maybe like that with a big sort of curl here. So this is how we'll denote semi-algebra with this curly S, and this is how we'll denote algebra A, and these are classes of subsets of your original set X. So the empty set and the whole set have to be in them, both for semi-algebra and algebra. Then it has to be closed under intersection. So if you take any two elements in this class and intersect them together, it has to be back in that class. It can't give you something that's outside of the set of subsets. And that's true for both semi-algebras and algebras, that they have to obey that one. So 1 and 2 are the same for semi-algebras and algebras. It's 3 that changes. For a semi-algebra, it's weaker. It's that any element in the semi-algebra, if you look at its complement, it must be buildable out of things that are in the semi-algebra. It must be buildable out of a finite disjoint union of subsets that are in the semi-algebra. Whereas algebra is far more simple than that. It just has to be the case that the complement is in the algebra. In fact, I'm going to change that. So, as I say, for a class of subsets that is an algebra, we will denote it by curly A like that, rather than by S, which we'll use for semi-algebra. Now, before we finish, let me just give you an example of a semi-algebra that's going to be a bit more relevant to what where we're actually going with this. So we'll take a set X that is actually a set that we're aiming for, like a subset of the real line. So we'll make, oh, not red again. Let me just rub that out. Go back to white. So we'll make the set X, we'll make it the interval from 0 to 1 in the real line. And I want to show you a subset of the power set of this that is a semi-algebra. So I want to show you a semi-algebra of this interval, this closed interval of the real line. Oh, and I'm making that a little bit too curly. So I'm going to show you a oh no, this has gone horribly wrong. Don't know how to do this nicely. Am I doing this? Yeah, we'll do it like that. Okay, so I'm going to show you a semi-algebra of this interval. So I'm going to define it. So it's going to be built out of a whole bunch of things. So we'll need, I'm going to take intervals that are going to be half open, half closed. And we're also going to need the intervals that go to the ends as well. So firstly, that's just so that we don't forget them, put in the empty set and the whole set. We know that for a semi-algebra it has to contain that. And then I'm also going to have, this is where it gets a bit more complicated. I'm also going to have all the intervals of the form 0 to A, and we'll go to A closed. And in fact, actually, if I do this so that it includes, just thinking, yes, we'll have A can go from 0, so it's going to be greater than or equal to 0 and less than 1. Or in fact, if we make it less than or equal to 1, let's give ourselves some more space. So if we take all of these intervals where A is greater than or equal to 0 and less than or equal to 1, I think it's fine for us to include 0 at the lower end. We might have to change that if we get problems, but I think it's fine to include that. Then we can take out that having to include the whole set separately, because it's going to now be included in all of these intervals. So I might try and write this out a bit better. So we'll have this set union, then the set of all these intervals such that A is between there, and then we'll have the some more things. So we're going to have all the intervals that are going to be open one end, A, and closed the other end, B, such that, and then I think it's going to be fine for A will need to be strictly greater than 0, or in fact, no, it could be greater than or equal to 0, I think that's fine, and it's going to have to be strictly less than B, which then can be less than or equal to 1. So let's just have a look at that, because I think that if we union this and this and this together, I think that's going to be the set that I want. So let's see if this is going to be a semi-algebra. I think we've got a little bit of degeneracy here because we've got the same set included twice, because A could be... Oh no, we haven't. That even if A was 0, that wouldn't be the same set. Fine. So let's see if this structure which I've built, which is a bunch of subintervals of my overall interval, is this going to be a semi-algebra? And this is actually... This sort of example is where the definition for semi-algebra is motivated from, because the whole point of measure theory, it comes from trying to formalize notions of like length and area and volume in the real world, starting with the simplest case, which is length. So we take the real line and we want to formalize the notion of length. So we know what the length of an interval is, and the idea is that we want to extend that notion to as many sets as possible. We want to kind of talk about, you know, if you have the real line here, we know about what the length of an interval is, but what if you have some much more complicated subset of the real line that looks more like this, spots all over the place? Can you talk about what the length of that subset is? We can talk about what the length of an interval is, we all know about that, but what about the length of more complicated sets? And that's the whole idea of measure theory, that we're trying to generalize this notion of the size of a subset of the real line from just intervals where we know it to more complicated sets. And it's the problem of trying to do that, and it's much more complicated than you would think. It's not as easy as you would think. Because the dream, of course, would be to be able to extend it to all subsets of the real line, but to do that in a sensible way is not possible. And later on in the playlist will show that it's not possible to do that in a sensible way. So we're trying to generalize it to as large a category of subsets of the real line as we can do. And that's why we're starting with these special types of classes of subsets. And basically semi-algebras, the motivation for the definition of a semi-algebra is that it's special classes of subintervals from the real line where length is nice and beautifully understood. And then the idea is that we are going to extend these semi-algebras to algebras and then to sigma algebras and try and extend the notion of length in a sensible way as we extend the class of subsets. So this sort of example, a bunch of subintervals, is exactly where the motivation for the definition of semi-algebra comes from. So let's just see whether what I've actually come up with here actually does work. Is this a semi-algebra? So firstly, it does obey 1. I've made sure the empty set is in there, and I've made sure that the whole set is in there. As I say, in here, when you set A is equal to 1, then you've got that interval included in this subset, which is being unioned to make the whole semi-algebra. So that's fine. They are both elements of, and let me have another go at drawing curly S. S there. 2. Now let's see if we intersect any two things. So let's firstly think about intersecting any two elements in here. Obviously, if you intersect anything with the empty set, you'll just get the empty set, so that one's fine, so we can ignore this. Let's think about intersecting any two of these together. So they all start at 0, so you have 0 to A1 intersect with 0 to A2. Well, that's just going to equal the interval from 0 to whichever one is smallest. So the minimum of A1 and A2, which of course will then be another thing back in there. So that's fine. If you intersect any of those two together, you'll get something that's back in here. Then let's think about intersecting any two of these together, and then we'll do the cross case. So if you take, let's have A1, B1, and you intersect that with A2, B2, well, of course, this has multiple different cases. So if we draw a picture, here's the interval from 0 to 1. If you have your intervals like this, where they don't overlap at all, then the intersection will be the empty set. And that's a possibility. You know, this could be A1, B1, A2, B2 here. So they could have no intersection at all. Or you could have that one is contained within the other. So this could be your first one, and then your second one could be contained in it, in which case your intersection will just be that smaller one that's contained inside the larger one. So it will be back in the set again. And then there's the final case, which is that they overlap. So you have one like this, and then you have the other one like this. And then, of course, the intersection will then be this bit, but then that will be another one of these half open, half closed. In particular, one of these open on the left, closed on the right intervals that will be back in here. So intersecting any of these two together, again, it's fine. So now we just have the case of intersecting something from here with something in here. So if we look at 0 to A, and we'll call that A1, intersect A2, we'll call this B2 as well, just so that we know that it's with regards to the second interval here. So again, there are two options here. You could have 0, A1 here, and then A2, B2 here, and this is all inside the whole space, which is 0, 1 here, i.e. they have no intersection, in which case the intersection is the empty set. That's fine, that's back in our class of subsets. Or you could have that they overlap in some way. So you could have, in fact, that the second interval, A2, B2, is completely contained inside your first interval, or you could have that this is over here somewhere, and then the intersection, so if we had that B2 was instead over here, then the intersection would be all of this bit. So if it's completely contained inside it, then the intersection is just that second interval. If it's overlapping like this, then the intersection will be this bit here, so all of this, and of course again you can see that that's open on the left, closed on the right interval, so it's going to be one of these things again. So intersections are fine. I think I've gone through every single possible case there and talked through why the intersection is going to be back in our set S. So that's the second property done. Now let's check property 3. So firstly, I'll just show you that it's not an algebra, this collection of subintervals. So if I, for example, took, let's take a quarter to a half, that's going to be in there. I've set A equal to a quarter and B equal to a half. And what, of course, is going to be its complement, I really hate the curly S, I'm trying my best here. Its complement is going to be the union of 0 to a quarter closed at both sides with, and I could put disjoint union here, with, then we've got open at a half, closed at 1. So this subset is not back in here. It's buildable out of things that are in here because this is going to be a semi-algebra, but it's not itself actually in S. So that means that S is not an algebra, but it is going to be a semi-algebra because, as you can see, we have a disjoint union of two subsets that are both in here. So this is one of these, this is then one of these. And let's just go through the different, let's just make sure then that all possible things, their complements are back in here. So if we look at the empty set, its complement is the whole set, so we know that that's in there. A is equal to 1 is an example in this part of the set here. Then let's think about complementing one of these, or any one of those. So if we have the interval 0 to a, then its complement, i.e. the interval 0, 1, subtract it, it will be the set a to 1, like so, which will be one of these sets. B is equal to 1, a is equal to a here. So it'll be back in the set. So those things complement, their complements are actually back in the overall set. So they're the simple case. They're the case that actually meets the algebra criterion. It's these ones whose complement isn't going to be back in the set. So then, if we take the final case, AB, and take its complement, so the 0, 1 subtract AB, it's then going to be equal to the disjoint union of 0 to A, closed at both sides, with then B, 1. And of course, this is the case. We've said, we need to consider some special cases here. So what happens if A is equal to 0? Then you'll have 0, 0, but that is actually still in here because we allowed the case where A was equal to 0. That's just a singleton set containing 0, so that's fine. And then we need to also consider the special case of B is equal to 1. Well, in that case, you'll have open 1, closed 1, but it's just nonsense in that case, because if B is 1 here, you don't even need this, you just need this bit. So it's equal to this for B doesn't equal 1, and for B is equal to 1, it's just going to be 0, A, and therefore it's going to be actually in the set. It's not going to even need to be a disjoint union of two things in the set. It will be in the set itself. So overall, I hope I've convinced you that this thing that I've created here, this subset of the power set of the closed interval from 0 to 1, which is made up of subintervals, this is an example of a semi-algebra, and this is one of the more useful examples of a semi-algebra, one of the examples that's actually going to come up again in measure theory. Whereas, of course, the examples that I used to motivate it up here for this finite set, this isn't relevant. This isn't the reason that this theory was created. This was just simple examples to illustrate the concept to you. So I think with that, we'll finish the video here. Thank you for watching.